Hello and welcome to York Universe, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. I'll be one of your hosts this evening. I'm Dr. Alina Hyde, and I'm joined tonight by Professor Robin Metcalf as a special guest. We are broadcasting live from the Allan Carswell Observatory, located at York University in Toronto, Ontario, Canada. As a reminder, York Universe broadcasts every Monday night at 9 p.m. local Toronto time, or Tuesday morning at about 2 a.m. UT, if that's more your speed. York Universe works in concert with our online public viewing program run by our amazing observatory team. It goes for the exact same time slot, 9 to 10 p.m. local Toronto time. If you're by any chance not watching this live, you can always find us by going to our website at yorku.ca/science/observatory and follow the links to OPV online public viewing, or click on any YouTube link to go ahead and join in with the adventure and join in the live YouTube chat. Our broadcast is powered by and in partnership with astronomy.fm, the voice of astronomy. We are not currently on astronomy.fm, but we are still partners with them. If you have any questions or comments for our past shows or suggestions for future topics, you can always send us an email at observe@yorku.ca, and you can connect with us on Twitter with our handle at York Observatory or York Universe, and of course with Instagram, York U Observatory, and Facebook at Allan Carswell Obs. So if all of that is not enough ways to contact us, you can always see our website again for updates, and if you'd like to make a donation, of course, that's yorku.ca/science/observatory. We'll be monitoring the chat room over on YouTube for questions if you're listening to this live. We do have a not great weather tonight. It's quite cloudy. It is October in Toronto, which means lots of clouds out and about. But we have lovely stock images that we can show you and a really interesting show for tonight. So let me just go ahead and introduce our guest a little bit. If you haven't heard, Professor Robin Metcalf has been all over the Allan Carswell Observatory website as a recent astronomer in residence. That's right, this year, actually, just earlier this October. Professor Metcalf is a professor in the Division of Natural Science at York University, where she's been teaching astronomy for over 20 years. Robin's PhD research pertained to extragalactic astronomy, but her current interests are in the search for life beyond Earth and the implications of such a discovery on humanity. She does a lot of teaching and a lot of wonderful night sky and outdoors activities, and she teaches students to appreciate what the night sky has to teach us. So she's the perfect person to have on as a guest for tonight. So Robin, how are the skies where you are?
They're similar to what you're seeing. I'm actually quite close to, I'm in my office in the natural science main office. So same sky as you, clouds.
Lots and lots of clouds.
Yes,
well,
yes.
Fingers crossed for some movement in these clouds later on this week. It would be nice to be able to see something up there. We did, of course, just recently have a partial solar eclipse, which a bunch of our crew got a few pictures from the beginning of before the clouds moved in. And I don't think I've seen a good gap in the clouds since then.
Yeah, I actually got a quick glimpse of it. It wasn't supposed to be visible from where I live, but at about 1, it was just shortly after 1 that I looked outside and I could see it was getting sunnier. And I just ordered some eclipse glasses. They had come the day before, so I put them on and I could see the eclipse sun. And so I grabbed my family members, my 2 sons and my husband, and like shoved the nerd glasses on them and pulled them outside to show them, grabbed 4 more glasses, ran down the street to another family friend of ours that have 2 kids that love this kind of stuff, shoved the nerd glasses on their faces as well. And so they all got to see it too, but it was only clear enough for like 15, 20 minutes. I got out my camera. By the time I was set up, it was gone.
Yeah, I think we had about probably from all of our different observatory members all around the Toronto area, probably about an hour on and off, just before the maximum. So around 1 p.m., as you were saying. So the maximum
Right.
was at 2. And by then the clouds had completely settled in. And of course, I didn't even have my eclipse glasses with me. I was running outside with a pasta strainer trying to get a picture,
Uh-huh.
which is of course the other trick you can do. So no, don't look at the sun, folks. If you're going to be doing solar viewing, make sure you've got protective glasses or some sort of implement to make yourself a pinhole camera. And a pasta strainer works great. So I do have one
I've
picture
never
from,
tried that. That's brilliant. I have to
yeah,
do
yeah, yeah.
that next time.
Oh, it's
You,
anything with good holes in it will make a wonderful, wonderful solar viewer.
yeah, you probably saw our colleague Jesse Rogerson, who it was quite clear in Barrie, and so he posted a picture on his Instagram site. It's a really awesome picture
Ah,
of the
wonderful.
eclipsed sun with clouds around it. Like clouds always make your astronomical photos even more interesting.
Yes,
So it's a
yes.
great photo.
If you can get the clouds to part just enough. One of our observatory members, Paul Mackin, actually got a similar shot. So
Mhm.
it's if you're in the right place and you've got a good camera, you can do amazing things.
Yeah.
And actually, speaking of the sun, I'm actually going to use that to get us to this week in space and astronomy history. So we try to do a little bit of these every show. Today we'll probably just do 2 relevant, I think, this week in space and astronomy history. And I'm not actually going to be going that far back. So sometimes we get some very, very old historical things, but I'm only going to go back to 2003 because it's October and I've been seeing more and more Halloween decorations up all over my neighborhood. I thought it would be fun to go to October 19th, 2003, which was the start of a very special solar storm. So we're talking about the sun. Well, the sun is hot and it is a giant ball of plasma. And as such, it does occasionally get very, very active. And from October 19th all the way through until November 5th, back in 2003, the sun was playing kind of a spooky Halloween trick on the planet. And it released a series of massive solar storms in late October 2003. Some of which, not all, hit the Earth. And of course, this being, the spooky season, it made for some very exciting viewing. So this was a little bit of warning. So October 19th, they're like, oh, there's some action happening. But a few of them actually took solar astronomers and solar physicists by a little bit of surprise. There wasn't a lot of warning for the 3 massive and intense sunspot groups. So we had October 19th, our first hint, the first start of the solar storms that were to come. And October 26th, we had 3 massive intense sunspot groups on the sun's surface. And these sunspots look like little dark spots. If you've got a solar viewer and you can safely look at the disk of the sun, they'll appear dark. They're areas where the magnetic field has tangled up and they tend to release a lot of energy. And that means more flares, more prominences, just generally more of all kinds of interesting stuff. So there were 3 of these intense sunspot groups. The largest was over 13 times the size of Earth, and that's on the surface of the sun. So they had a bunch of complexity in their structure, and because of the large size, the sunspots were able to combine, and 17 major solar flares, including one of the largest ever recorded, went sort of whoosh off of the sun. So,
That is
I mean,
crazy.
it didn't make that sound, I'm sure. It's it was absolutely one of the most interesting events, I'm sure, astronomically in
Mhm.
2003. And this was because of the increased sunspot activity. So the solar activity all the way from the 19th to November 5th kind of originated from these 3 sunspot regions. And of course, because sunspot watchers and solar physicists do chart these things, they actually got numbers numbered by SEC forecasters. So they were regions, if you want to know: 484, 486, and 488. And each one of the regions was remarkable, as in larger than we normally see on our sun, in terms of size and magnetic complexity. So that means how tangled up was the magnetic field around them. In particular, region 486, which was the middle one I mentioned, was very, very significant. So this was over 13 times the size of Earth, which is still a tiny part of the sun, I might remind you. So this is 2,600 millionths, as in divided into a millionth of the solar disk. So still,
that is crazy.
The sun is gigantic. So this is the largest sunspot group observed since November of 1990. So, of course, this week in history is a sort of day for the record books and solar activity, and the fact that we had these three together. We had basically all kinds of little solar flares, and the largest ever recorded, that was on October 28th, which is, a couple of weeks away this week in history. This was the enormous solar flare that came out, and that solar flare is a fast-moving burst of gas and magnetic energy from the sun's outer atmosphere. So that's a bunch of very, very excited gas that's gotten all kinds of accelerated and roiled up, if you will, by the tangled magnetic field. And this comes off of the sun, and if it's large enough, it's what's called a coronal mass ejection, or CME, because astronomers love acronyms. And of course, once this was released from the sun, a geomagnetic storm did quickly follow, and that's of course a storm here on Earth that we can observe.
And were there recorded like communication disruptions and unusually intense aurora sightings? Seeing them at southern latitudes that you don't normally see.
Yeah, so this was a pretty intense event. As I say, back in 2003, we still had, this is not that long ago, so we are still very much in the digital age here. And this was the sixth most intense storm. So not the most intense storm, but the sixth most intense in the last 70 years. And so our records aren't great. Over 100 years ago, for probably obvious reasons. But with Earth's atmosphere trying to protect us from dangerous high energy particles that are produced by these solar flares, what happens is it hits our magnetic field, and our magnetic field sort of tries to deflect and protect, which is good. It stops our atmosphere from getting stripped off, among other things. But that means that we can get a lot more activity from aurora and from all kinds of things. Everything from satellites to GPS to radio communication experienced problems on this particular storm. And storms like this affect Earth orbiting spacecraft, and not just any, but if you can imagine where the sun is and where Earth is, it's going to affect about half of Earth orbiting spacecraft, i.e. the half that's not on the other side of Earth being protected.
Right.
So this particular storm disrupted satellite TV. So if you had a satellite TV in 2003, you would have seen a intermittent disruption. Also radio services, so radio reception, radio broadcasts, and it did actually damage a Japanese science satellite, unfortunately, beyond repair. This activity, yes. So it actually had a bunch of long-lasting carry-on effects.
And a lot of calls to Rogers.
Yes, lots of calls to Rogers, probably radio broadcasts that didn't get completed. They actually sent several deep space missions into safe mode or complete shutdown. And at the height of the storms, astronauts in the International Space Station would have to actually take cover from the high radiation
Wow.
levels.
Hmm.
So our astronauts would have to worry. Airplane flights also. This particular storm was large enough. It had communication problems for several airline flights. Nobody crashed, thank goodness, but they did have communications blackouts. And the worst communication blackout that I could find for this storm was Antarctic science groups who had
Hmm.
a full communication blackout for 130 hours.
Wow.
Full communication blackout. So GPS systems went on fritz, deep sea and land drilling had problems. So this was definitely tricks and not treats played on our
Right.
technological system for the great Halloween solar storms of 2003. The
Interesting.
the treat part came when we had prolonged geomagnetic storms, which brought aurora. And that's what you were
Right.
asking before. We had a middle and even low latitude aurora on October 29th and 30th. So how
Hmm.
spooky is that? So we had aurora sightings in Toronto. We had aurora sightings all the way down past Toronto. If you keep going south into across the US, all the way down to Florida. People in Australia, Central Europe, tremendous aurora viewing. I did not see them, so I'm just like, what was I doing in 2003? Where was
Me
I?
neither. I'd have to think about
Um,
where I was. Hmm.
how did any of us miss this? But I didn't see
Yeah.
it.
Yeah. Yeah, in my history of astronomy class, we talk about, historically notable aurora events. And another big one is what's called the Carrington event in 1859. And it's given that name after the British astronomer Carrington, who was the first to see the solar flare. And so it was the largest measured geomagnetic storm to date, and it resulted in aurora seen as far south as the Caribbean. So, like, there were reportings of it in Cuba, southern Mexico as well. And a while ago, I dug up the report from a Mexican newspaper. And so there's a quote from the newspaper describing what witnesses saw. And so the description was, a beautiful translucent white cloud that showed a carmine red background spreading throughout the Northwest, which was divided into various groups with growing intensities. So pretty dramatic. And I've always wondered, like, this is back in 1859, and when aurora were seen from these latitudes at places that, they were really never seen, what did the people think was happening, right? Like, it must have been extremely alarming. Most of the people that witnessed the aurora would not have ever heard of the phenomenon. And this is pre-internet, right? So you can't just be like, hey, Google, hey, Siri, what's going on in the sky? It would have been quite a while before anyone, understood what exactly was happening. So, and just interesting time.
Oh yeah, and it's worth remembering as well. This is what you mentioned, 1859.
Right.
So that was 1 to 2 September 1859, and this was really the strongest one we had a chance of recording, because in 1859 there were only just enough technological and electronic devices to be disrupted.
Right, right.
And telegraph systems, in
Hmm.
particular, were disrupted, and telegraph pylons were throwing sparks.
Hmm.
And in a very interesting one, this storm is different from the Halloween storms in its strength, and one of the ways you can see that was the amount of charged particles that it put into the air actually succeeded at something that has become very famous in recent times, wireless power. To the
Ah,
extent where there were telegraph operators
oh, that's right. I
who
remember, yeah, hearing about
remained
this.
remained connected
Right,
even without power. And there's actually there's a one that was reported in 1859, reported in the Boston Evening Traveler, and it's worth repeating because it's Boston operator to Portland operator.
right,
Please,
right.
please cut off your battery entirely for 15 minutes. Portland operator will do so. It is now disconnected. Boston says, mine is disconnected and we are working with the auroral current.
Right.
How do you receive my writing? And
That's
then
amazing.
the Portland says, and I quote, better than with our batteries on.
Oh my God, that's so cool.
Right? And so they had this whole conversation powered
By an
by the
aurora.
current that was
Hmm.
induced by the aurora. And if you can imagine, that level of current is not enough that it would cause you personal harm, but your electronics today would be
Right.
so sad. Like anything, any modern electronics not in like a Faraday cage would be extremely sad. So maybe some car systems would probably be all right, I guess. But anyways,
Right. That's
um,
such a cool story.
yeah, and this is one of the things is how many times would this have happened before 1859, where people would just have not noticed and
Sure. Yeah.
been like, huh, that's a funny cloud. Oh well,
Hmm.
you know. Um,
Amazing.
anyhow, yeah, very, very fun stuff.
So
Absolutely.
I've never seen an aurora. Have you ever?
No, I have not. Despite being in Toronto now for almost 4 years. So
Right.
I am counting the clock here. I'm like, all right, come on, son.
For the coming
Um,
solar maximum.
yes,
So,
exactly.
so interestingly, there is when you look at models that like extrapolate the coming peak, and at the moment, the prediction is that it's going to occur in 2025, right? I can't remember the month. Do you? It's
Oh, the 2025 sounds about right.
okay, anyway, it doesn't matter. So 2025, but if you look at the prediction compared to the actual number of sunspots that have been recorded in the recent years, then what you see is that the actual sunspot number is higher than predicted. And that could mean two things. It could mean that, in fact, the solar peak is closer than anticipated. So it could be 2024. Or it could be that the timing is correct, but that the intensity of the predicted peak is too low. And that, in fact, the peak will occur in 2025, but that the intensity will be higher than predicted. So more sunspots, more storms, more aurora. Either way, it's good.
Yeah, yeah.
Well, good for
So
people that like to look at the night sky, not
yes,
so
and
much for, communications people.
well, it might be all right for them. It really is only very extreme events that we do see
Sure, sure.
communication difficulties. And I have checked. So if you're thinking 2025, you wanted to narrow it down, the estimates are July, but
Okay.
the error bars are 8 months.
Oh,
So
okay.
so there's 16 months around July where they
Right.
so
And I mean, and it's
um
already started that
yeah.
like we're seeing more and more records of people seeing the aurora from, southern, like around southern Ontario, which is quite unusual.
Yeah,
And
and hey, maybe we have a good chance. Next year we also have the total solar eclipse. So how cool would it be if we had
oh,
aurora
wow.
and
Yes.
like I'm just saying, I'm just gonna wish this into being a total solar eclipse with aurora. Let's make it happen.
That would be so amazing.
Let's like, come on, Ontario, we can do it.
Yeah. So given though, like that there's been all of these photographs that are appearing in the papers, and also, so I'm a member of the Royal Astronomical Society Mississauga branch, and the members all email around their photos. And so over the last few weeks, some of the members have been showing photographs of aurora that they've taken in around our latitudes. And the photos, some of them are just spectacular, like pinks and reds, and they just look so amazing. And me having never seen an aurora, I don't know what to believe. So I see those photographs. I'm like, okay, well, that's what it looks like. And so I recently saw one of those photos and I sent it to a friend of mine and said, look at this amazing photo that someone in my little observing group took. And my friend who actually has seen aurora from around these latitudes said, no way, that's not what they look like to the naked eye. And so he said, go back to the photographer and ask him what he actually saw compared to what he captured in the photograph. And so I asked, and it turns out that the view through the naked eye is quite, the view captured in the photograph is quite different. Because through the photograph, you can take long exposure pictures, right? And so you can capture more light than the eye can capture on its own. So he did tell me the description with the naked eye, which was still quite wonderful. He described it as visually there was a light green yellow glow along the horizon, which was continually shifting. On top of this appeared huge white pillars, which slowly appeared and disappeared as they moved from right to left. The movement was very noticeable, especially during the height of the storm where the lights were in a continual state of flux. And then he ended by saying, a symphony of light rising up from the horizon and dancing across the northern sky, which was quite beautiful. So that was the naked eye view. And then this was from a photo taken, I think 3 weeks ago from near Orangeville. So like an hour's drive north of Toronto. And then I followed up and I said, okay, so could you see any of the pinks that you show in the photograph? He said, no, that the photographs were 20-second exposures. The reds and pinks were not visible, but that they appeared in the photos like a diffuse glow. And he just did a tiny bit of post-processing. So he boosted the saturation setting just a tiny bit. And once he did that, that's what caused the reds and the pinks to pop out quite a bit in the images.
Yeah, and that's really
so,
worth remembering.
It's important to know the difference and like what we can actually expect to see at these latitudes.
Oh, absolutely. And that's absolutely true of really any astrophotography you ever see. It's almost always processed.
Right.
And so when you see beautiful, detailed images of galaxies, it's usually not what you would see with your naked eye. So if someone has done minimal processing or no processing and left the filters off, you can get what's called an eyepiece photograph, or you can actually take a picture through an eyepiece of a telescope with minimal adjustment, and that gives you a more realistic view, but they're almost always a little less I wouldn't say less spectacular, but they
just differently spectacular.
Less colors, less shapes, less vivid structures. And so if you're pulling out structures and you're interested in analyzing them, as astronomers often are, you need to use these techniques to get the information out, and you make these spectacular pictures. But it is very much worth noting is like, you don't see these beautiful pictures of galaxies when you look at Andromeda Galaxy with your naked eye, for example.
But not
Aurora.
Not to minimize the live naked eye experience, because that brings in different perceptions that you don't capture from just looking at a photograph on your phone later on, right? Being in the moment, as speaking from someone who, likes to go out at night and take pictures, being in the moment and in these remote places, not a lot of people around, and seeing cool stuff in the sky has its own amazingness to it.
Oh, so, there's nothing.
I highly recommend
it. Seeing it with your own eye is the best. Like, absolutely. And it's as you say, it's a different kind of magical, and it's not something you can capture on camera.
Right.
And that's something that's always worth remembering. Is something extra special about being able to see it, for yourself, with just a telescope and or just naked eye and the aurora. I've seen hundreds of beautiful pictures. I would still love to go see them.
Oh, me too. It's like huge bucket list for me.
Absolutely.
And I'm sure that looking at all the photos don't at all compare to the actual experience of having it all around you. just the surround experience must be absolutely amazing.
Yeah, and it is worth noting that if you do go see aurora, the colors that you see are actually due to different elements in our atmosphere. So the Earth's atmosphere is currently about 78% nitrogen, 21% oxygen, a small amount, 0.93% argon, and a very small amount but significant, 0.04% carbon dioxide. We have neon, helium, methane, krypton, ozone, and hydrogen, as well as water vapor. And those elements actually interact with the charged particles or the electrons, which get excited. So the incoming energetic electrons excite the elements of that are in the atmosphere, and depending on where it hits, it will excite things that are higher or lower in our own atmosphere. So, for example, the color of the light depends on the color of the element that it hit, basically. So the most common aurora color is green because our eyes are actually attuned to see green very well. We're sensitive to the green color spectrum. And green auroras are produced when the charged particles collide with high concentrations of oxygen molecules, and that's around 60 to 190 miles or 100 to 300 kilometers. So it's color that we're attuned to see, and it's an emission that's likely to happen. Red aurora, as you mentioned, red was something that your colleague did not see with their eye. They're less frequent, and they're associated with really intense solar activity. And your eyes are not as good at seeing it. So that red will occur if solar particles react with oxygen at higher altitudes. So you have to go up to 300 or 400 kilometers rather than 100 to 300. So you have to get above that higher altitude, more excitement. And red auroras are often seen kind of at the edges of an auroral display. And it's it's a higher frequency making that red color visible. So it's very unlikely. If you do actually see red, count yourself very, very lucky. Even more uncommon is actual blue and true purple. Those are when you get particles colliding with nitrogen at an altitude of 60 miles or less. And they're extremely rare, sometimes seen on the horizons. You can get yellow and pink as well, and that's usually a mixture of red with green or blue if you've ever done paint mixing.
Interestingly, though, that the friend of mine that says that he has seen aurora from around here is that he says it mostly looks like a whitish glow. So I didn't know what to make of that.
Well, I would guess that they're
Like
probably
mixing.
just seeing, or just seeing a very, very faint blue.
Could be, yeah.
It's could be. And the white color would also come out from mixing as well, so that would make sense. However, this is about the point where we're about halfway through. I need to remind everyone that you are in fact listening to York Universe, broadcasting live from Allan and Carswell Observatory, located at York University in Toronto, Ontario, Canada. If you'd like to find out more about our broadcast or join any of our other programming, you can always see our website at yorku.ca/science/observatory for chat questions. And if you have anything you'd like to post to us on social media, you can find us on Twitter, Instagram, and Facebook at Allan and Carswell Observatory. Tonight, you're listening to Dr. Elena Hyde and Professor Robin Metcalf, and we are discussing all things solar activity, I suppose, but mostly aurora. So if you can always tune in with us anytime you like, as these episodes are recorded on YouTube. And if you'd like to swing by later on from any other shows, or you'd like to see the archive, again, that's the same website from before, yorku.ca/science/observatory. Right now, we are live on OPV, so you can also join in the YouTube chat and ask any questions to our amazing online public viewing crew live on YouTube now. So make sure to head on over and check out some of the wonderful archival images that they're showing right now. All right. So, picking up off of the sun, I think we have time to switch gears here and get into a little something different. So we're actually going to go back one more this week in space and astronomy history, which will get us onto another really interesting topic, I think, and that is going back to the 20th of October 2020, which is really not that long ago, but it's still in the past, so it counts, and it's close to today's broadcast. So back in 2020, OSIRIS-REx touched down on Bennu, and if you haven't heard about Bennu, you must not have been watching very much astronomy news, because a recent sample return has just occurred. Real material from the asteroid Bennu, or 101955 Bennu, if you would like the official name, has returned to Earth. So this is our first official asteroid sample return. All the way back in 2020, the OSIRIS-REx spacecraft was touching down on Bennu and successfully collecting a sample. So that sample, of course, had to be brought back to Earth. If you haven't heard of OSIRIS-REx yet, this was a NASA asteroid study and sample return mission. It went to Bennu, as I say, back in 2020. The material returned in September of 2023. So this is very, very recent news. It was extremely exciting. We talked about this a little bit last week as well, but it was quite something to see everybody run off to the helicopter and chase this sample capsule down.
That's so amazing.
Once it landed.
What a moment.
It was so exciting for so many reasons. And of course, since then, it has been very carefully traveling around, wrapped up in multiple, clean containers, so that it could be analyzed. So a little bit of history as well. OSIRIS-REx was actually launched all the way back in 2016. It flew past Earth in 2017, and it actually rendezvoused with Bennu on 3 December 2018. And it wasn't until 2020 until it actually got the sample. It spent the whole 2 years in between analyzing the surface of this asteroid and trying to find a suitable site from which to extract a sample. And because this is kind of it was the first time that they had done an asteroid sample, they really, 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 really wanted to get it right. And so they're like, we have only one chance. It had only one ability to get a sample. It has only one sample container, and they absolutely had to find a place where they were really sure that they would be able to grab some material off of Bennu. And Bennu is a very strange object. It's a rock in space. It's not particularly large. It's it's got it's about 500 meters by 500 meters by 500 meters. It makes it sound like it's a square, but it's actually sort of the shape of a diamond, like a chunky diamond. Not completely with no smooth edges. It's all sort of smushed around, and there's craters in it. And
A
it's got
square would be terrifying, like a Borg cube.
Yeah, a square would be a Borg cube. That would be a little suspicious. This one just kind of looks like a dusty diamond. And it's not round because it doesn't have the gravity to pull itself into a circular shape like Earth does. It's not particularly big, so it doesn't have a lot of gravity at all. And it seems to be really low density. And the more they studied Bennu over the 2 years that they were in orbit, they were actually able to find out a lot about its density, to study it and to study its surface. And they found that it was actually sort of shedding particles, kind of like it was little bits of rocks and things were just continually flying off of it.
Yeah, that was
So
a really interesting part
yeah.
of the shoveling event, when they found that they were expecting more resistance from the shovel.
Mm-hmm.
And so that gave us a picture that in fact it's more like a rubble pile. Although it's suspected to have like a denser core, but at least it almost has an atmosphere of rubble. is a cool way to think
Yeah,
of it.
or some sort of hollow, low density. And so the idea was, of course, that since Bennu is in an orbit that does take it across what we call the ice line, so ice would want to evaporate. Maybe it was kind of being held together by a lot of ice, and that's getting evaporated off the surface, and then the little rocks are flying away. And maybe it's really, really water rich. And maybe if it's really, really water rich, these kinds of things, these rocks in space, might be a way to study how Earth was formed and how Earth got its water. And that's because it was chosen as a target of study as kind of a time capsule. So it's thought that not a lot has happened to it since the beginning of the solar system. So it would have basically stayed the same. Like I said, water would have started to evaporate, or any ice that was there would have started to evaporate. But whatever it's made of would have been roughly whatever the solar system was made of when it was formed. And so by grabbing up a scoop of it and finding out what's in it, oh boy. Very, very
Amazing.
exciting. And as you say,
Hmm.
the sample collection went even better than they thought. They had an easier time digging up the sample, but they did not know how much they had until it
Hmm.
came all the way back this year. And even after the capsule had landed, they had to wait until they had completely opened it in the super safe clean room
Right. So
until they actually knew how many grams they had.
yeah, so I can tell you an interesting story about that. For people that have been following along over the last week, you might have come across the name Kim Tate in local newspapers. And Kim is the curator of mineralogy at the ROM here in Toronto. And she's also a member of the team that gets to decide which slice of Bennu is going to come to Canada, to the Canadian Space Agency, so people can study it here. And I met Kim about 5 years ago because we both played women's recreational ice hockey and we were on the same team. And so, aside from, she's really an amazing person. Aside from being now sort of a curator of the solar system, she's got 5 kids, 2 sets of twins. 4 of the kids are, well, they all play hockey, but 4 of them are goalies. And as a goalie mom myself, I can attest to that is like absolutely insane. Like just having one goalie kid is a physically and emotionally exhausting experience. So she has 4. Anyway, so Kim was at the Johnson Space Center in Houston the day after the sample arrived on Earth. She missed the actual landing because 2 of her kids had a hockey game that day. But I had a quick text chat with her just over the weekend, and I asked her something about the mass of the sample that had been bugging me ever since the press conference that they had last week. And at the press conference, 2 members of the press asked the panelists questions along the same lines as, why haven't you measured the sample mass precisely yet, now that we have the sample now that the sample is on Earth? And so going back a bit, when the sample was first collected on the asteroid, one of the first tasks that the craft was supposed to do was to measure the mass, because that was the big question, right? Like how much did they get? But they couldn't measure the mass at the time because they took a picture and they saw that the lid wasn't sealed all the way because there were some big pieces of asteroid that were preventing the lid from closing. And they could see in photos that some of the sample was leaking out of the capsule. So they thought, okay, we better not do the mass measuring maneuver. Let's just get this thing home safely and then we'll deal with it when it gets home. So then shortly after that, someone came up with this cool way of estimating the mass in flight. And basically they measured the change in the moment of inertia of the craft based on maneuvers that had been done before the sample was collected and after as well. And so they got a rough estimate of 250 grams, but it wasn't precise. So 250 plus or minus 100 grams, which was still exciting because I think the target was 60 grams. So even at the low end, that was, huge success. But anyway, that was just their imprecise estimate. Fine. We get the thing here on Earth. And then they, they've got it in the glove box, which is that, sealed and safe place. And they see that there's this extra asteroid matter that had collected around the lid. And so this was awesome. It was like extra sample. And it gave them this amazing opportunity to kind of do a dress rehearsal of doing all the science that they want to do on the sample and making sure that all the processes are in place before they actually get to the actual sample. So, the question was asked, why didn't you just, why yet do we not know exactly how much mass is in there? And the panelists answered the question by saying, well, we've spent all this time with all of this extra sample that we got, which turned out to be something like 30 grams. And so we haven't yet gotten around to measuring the mass. And when I heard that, I thought that sounded really strange, right? Like, why not just measure the whole capsule? Why not just weigh the whole capsule and then subtract the mass of the empty capsule, right? Like you don't need to open it in order to get at the precise mass. And like if you're a conspiracy theorist, which I'm not, but if you were, you might think like maybe they're hiding something. Maybe the capsule is empty. Why haven't they made this mass measurement? Okay, so I asked him this over the weekend, and her answer was that the reason why they didn't measure the mass in the way that I just described is because the capsule is too heavy and the scale that they have in the glove box doesn't go that high. So I thought about that and I looked up the weight of the capsule, the mass, and it turns out that it's only about 45 kilograms, right? So like 100 pounds. So I asked him, like, why can't they just borrow a scale for my bathroom, right? Like, 100 pounds, that's not a huge amount. And so her answer was, which I thought was really interesting and totally believable, is that it's because the equipment that they have in the glove box, it has to be constructed from materials where you can't have any contamination. So there's a very strict range of substances that you can use to build your instrumentation with. And so many of these instruments, like a mass scale, had to be redesigned using these limited substances. So for example, no plastics allowed in the glove box because plastics, they can be affected by temperature changes. They can, degrade and stuff and contaminate the sample. So if you think of your bathroom scale, my bathroom scale, it will only measure my weight out to 1 digit after the decimal, right? So when you're talking about weights like 100 pounds, you can't measure that as precisely as you can if you've got a small weight scale that can measure small amounts like asteroid samples, right? So if you've got a limited amount of materials to design your weight scale, it makes much more sense to design a very small one that can measure things very precisely than use up your space and resources with a big one. So that's why they haven't yet measured the mass yet, is that they really do need to wait until they can open up the capsule and put the actual sample onto a scale. So I believe it.
Very nice. Well, it does make sense because speaking, from a Canadian perspective as well, we're going to be getting 8% of this mass,
which is amazing. Yeah. So the more the better.
If you have 100.56832 grams, and you only record 100 of that and then divide it up, then there's a whole fraction of a gram that you could be getting a percentage of that you're not getting.
Right. Exactly.
So from our own perspective, as people who are going to maybe not directly get access, well, maybe Kim will, but not directly get access, but it's coming to Canada. We should let them definitely measure it as accurately as possible. And I have to say, with the story, the one thing I'm wondering is, I really want to know what happened to the material that was evaporating out. Like they must have captured it somehow. I want to know where that gas is. I want to know if it's gas and they've actually managed to capture it. There's all kinds of cool like laser-based spectral analysis you can do. I was just like, oh, of course they captured it, right? Like, but I don't know. I don't know if they did or not.
Uh-huh.
So now we have even more important questions to know.
Yeah, it's amazing. It's just an amazing thing.
All right. Just a little tiny note. I did actually forget one of the reminders for this week. So if you are still listening and interested in current event reminders, we do actually have a last atrium tour for the Allan Carswell Observatory happening this Wednesday. That's the last atrium tour of the season because, as everyone in Toronto has noticed, it is starting to get rather chilly. So this Wednesday, we'll be going out to the Arboretum parking garage roof for the last time in the 2023 season. If it is clear outside, please do come along and join us. The ticket links are on the website from before. Last chance for the season, so double fingers crossed given how cloudy it is today. Now we have time for, I think, probably one of the news items that I was thinking about doing. I'm like, oh, we've got about 10 minutes left. So it might be fun to actually do a little bit of a magnetic. Gosh, should we do the magnetic or the solar one? What's your vote, Robin?
Oh, doesn't matter. Magnets are cool, if you're a Breaking Bad fan.
I haven't seen it, but
Oh, okay. Sorry. There's a
magnets.
cool episode all about magnets, but yeah, go ahead.
I definitely agree. Magnets are awesome. I love magnets. Magnetic levitation is probably my favorite.
Oh,
But
cool.
since we've been talking about magnetic fields and how important they are, the incredibly active magnetic field of our sun getting tangled up is, of course, what causes all of the flares and coronal mass ejection and aurora here on Earth. But it does actually affect, the moon a little bit, interacts with some of the moon's surface rocks. But the moon itself actually does have ancient relics of magnetism. Our Earth's moon, that is, just to be absolutely clear. So this is a recent news article that came out in October 11th. So that was 5 days ago from Stanford University. They were looking at the magnetism, sort of the magnetic relics, I should say, inside the moon or moon rocks, and whether or not a spacecraft and traveling to the moon might disrupt the magnetic signature in moon rocks. So will this happen? So they did a study on this, and they found that you could remove spacecraft contamination for lunar samples. And that's basically looking at magnetic spacecraft contamination. So for things like the moon, it's not active right now. There are no volcanoes on the moon, but there used to be a long, long time ago. The moon's magnetic field, likewise, is not active. So magnetic field of Earth is powered by the liquid magma inside with the core. It's very, very fun stuff, actually. But if you don't have a liquid core, powering your own magnetic field is pretty hard, actually. You can have a residual magnetic field, like those bar magnets we stick to our refrigerators. And that's all that's left when you don't have lava, basically, or liquid rock or plasma in the case of the sun. So the moon's ancient magnetism has been a mystery for quite a while, with the sort of studying how it used to happen and looking at lunar rocks. So different kind of sample return. Of course, I expect that Bennu's samples will also be tested for any residual magnetic field, because that would be very interesting. But the lunar samples would have a basically now deceased magnetic field. It might have been active for about 1.5 billion years after formation, give or take a billion years. So we don't really know how long the moon had a magnetic field for, but it was enough to impart some magnetism into the moon rocks. And we think that early moon would have been very, shall I say, hot. Yes, hot, liquid, and could have had a liquid core. So its magnetic field early in its history, so long time ago, would have been generated like Earth's via a dynamo process. So you'd have churning and spinning of conductive liquid metal within the planet's rocky core, and that would generate your magnetic field. That's how it works on Earth. On the early moon, it probably would have worked the same way. But researchers have been wondering how such a small thing as our moon could have sustained a long-lived magnetic field, and whether or not the return samples that they're seeing, that point to an existence of an ancient dynamo would have been acquired basically. So this magnetic signal, could that have been acquired basically due to strong magnetic fields on board a spacecraft during the return? So is a spacecraft somehow imparting a signal to the moon rocks? Or, alternatively, you could maybe do some sort of plasma being produced by a massive impact, a really big crater. But at least now we know, so thanks to this article, that the magnetism in lunar samples that we've seen is not going to be altered by spacecraft journey back to Earth or certain laboratory procedures. So a lot of the tests that have been done can be ruled out as having affected the lunar rocks. So this means our ancient dynamo theory has a chance. It's not saying that it definitely happened. It's just saying that it looks like it could still have happened. And now we know at least that the spacecraft returning the samples is not going to magnetically fry our rocks.
That's so interesting, especially because you mentioned Bennu, and at the press conference, a high school student asked the question of the panel, what are we going to be able to learn about its magnetic field? And the answer was that and asking questions about the magnetism is not in the list of science priorities because there's so much magnetism involved in the spacecraft and also in the instrumentation that they figured that any magnetism would be contaminated by these external fields. So who knows what will happen? I mean, the other thing that the panel says is a great thing about having a sample on Earth is that we can, in 10, 20 years from now, we can ask questions that we don't have the technology to answer now. So maybe in 10 to 20 years, they can figure out a way to learn about the magnetic field, even if there is contamination.
Yeah, it's an interesting question. What would it mean if an early solar system item like Bennu, who obviously has never had, there's no way it's ever had a lava core. No way. If it had a magnetic field, how could it have gotten that? What would that mean?
That would be really interesting.
I know. And so now they know, and this is again thanks to this the same study, that basically they tested with magnets. They actually went ahead and exposed samples to a field strength of 5 millitesla, or 100 times stronger than the Earth's magnetic field, for 2 days. And that's approximately the length of a return journey from the moon. Then they took the samples into a magnetically shielded room to measure how quickly the contamination decayed and how easily it could be removed using standard techniques. And so they were able to show that basalts, like what's on the moon, this is rocks formed by the cooling of lava flows, they're less susceptible to acquiring magnetic contamination than glass-bearing rocks. And so your general basaltic rock, which is just, it's just one of the most generic rocks out there, that would be something that would be have any resulting contamination could be easily removed if it did occur.
That is amazing.
Which is interesting. So I thought this was a fun little one. Basically it's trying to establish lunar origin for these magnetic records in Apollo samples.
Very cool.
If it's true, maybe future Bennu magnetic field overlap or something. All right, so I think we're about at the end of our our ability to talk about news. So we'll have to save everything else for next time. And I will, any last notes from your end, Robin?
No, I'm good, but thank you so much. This was lots of fun.
Excellent. Well, thank you for being here. And everyone, you have been listening to York Universe, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Professor Robin Metcalf and myself, Dr. Elena Hyde. And of course, you can always find us every Monday night, unless it's a holiday, here at York Universe. And you can always connect with us over on Twitter at York Universe as well, or Allan or York U Observatory, sorry, Facebook at Allan Carswell Obs, and Instagram at York U Observatory. So just in case you want to reach out to us at any other time that we're not broadcasting live. Our website has show notes, content, updates, and more at yorku.ca/science/observatory. Thanks for tuning into York Universe. Clear skies, everyone, and have a good night.